What we're going to look at today are just some special cases, certain types of factoring and mixed factoring. Tomorrow we're going to start working with algebraic fractions, and they all rely on the ability to factor well. So we're just going to spend more time on factoring, more of the same today. There's a couple of things that I want to make sure you can do before you leave today. There's two main kinds of factoring that we're going to look at. We're going to look at one type of factoring called factoring by grouping, and we looked at that just a little bit on Friday when you use the grouping method to factor trinomials. That's like the AC factoring that I showed you. You did a little bit of factor grouping when you did that. We're going to do a little bit more of that today. And then the other main type of factoring that we want to look at today, it's a special case, is if you have the sum or difference of two perfect cubes. Now we did difference of squares on Friday. If those are cubes, you can also factor it, even if it's addition instead of subtraction. That's where we want to turn our attention. We're going to start out with factoring by grouping. Now the criteria for factoring by grouping is kind of strange. We'll take a look at that in just a second here. The thing that tips you off to factoring by grouping usually is that there's four terms. But there has to be an even number of terms. Now, we'll just consider an even number of terms. If you've got an even number of terms, it might be possible to factor just half of them. That's why you have to have an even number, because you can factor exactly half of them individually. And if you do that, it's factoring by grouping. The thing is that you want to rearrange all of your terms so that the first half all contains some common factor. So let's look at an example of this. It's easier to see in an example. Let's factor this thing. Well, the first thing you have to do is you have to make sure that you rearrange them any way you want, but you want to rearrange them somehow so that the first half of them all have some common factor. Usually, the back half, the second half, will also have some common factor, but that doesn't have to be the case. The first half does have to have a common factor. Well, and we're starting out with a simple example here. They're all set up so that that's the case. If you look at your first two, what's your common factor of the first half? 4x. Now, as it turns out, the second half here also has a common factor of 6, right? 6. So what you do is really kind of like what we were doing on Friday when we were factoring trinomials. You picture it as two separate halves. Okay? Now let's factor the left half. We can factor, as you said, 4x out of the left two terms, and we get 4x times. If we factor that out of these two, we're left with 2x plus 7. Plus, we factor the second two terms, we can factor out a 6, and we're left with 2x plus 7. Now, not any four-termed expression is going to factor by grouping. We won't have accomplished anything unless, after you factor by grouping, these two factors inside the parentheses match. And if they do, now it kind of looks like what we were doing on Friday. We can factor this out of both of these two terms. This term has a factor of 2x plus 7. This term has a factor of 2x plus 7. We can pull that out to the back. So what are we going to be left with in this term? The 2x plus 7 we're going to pull out. We're going to pull that out of both of these. So this term only has left the factor of 4x. This term only has the factor left of 6. And then those are both multiplied by 2x plus 7. Now this is factored, but it's not completely factored. Drew's right. Drew noticed that you've still got a little bit of factoring here, a greatest common factor right here. Now you wouldn't have to have waited until here to do it. You could have noticed it way back in the beginning, and it would work out fine too. But ultimately, factoring is a factor now or factor later thing. The factors will still be there regardless of where you do it. So we can factor that 2 out, and we finally end up with 2 times 2x plus 3 times 2x plus 7. And now it is completely factored. And that's our final factorization. Okay? Now, again, we should, and we will in the next example. Factoring is the kind of thing you can always check yourself and know if it's right or not. We could FOIL these two out, distribute in the 2, and we better end up back with that original expression. We won't do that in this one. We will in the next one just to save some time. Okay? Now that should look familiar because we had to use that principle on Friday. Now we're going to look at some uglier cases, though, where that doesn't shake out quite as nicely as that, but that's the principle. Let's do another one. Let's factor negative 3n squared minus 8m plus 12mn plus 2n. Okay, well, first of all, does it qualify for factor by grouping? Even number of terms, yeah. But that's not good enough to qualify for factoring by grouping. What should we do here? Anything jump out at you? What has to be true about the first half of the terms? There's got to be some common factor in the first half of the terms. That's not the case here. 3 and 8 have no common factor. N squared and m, well, I guess there's a common factor of negative 1, but that really doesn't get us anywhere. Okay? So how do you want to rearrange these so that we can have two terms out in front that have a common factor? We could move the 12mn and put that in this spot. Then we'd have a common factor of n, right? In fact, 3n. The problem with that is if we leave that, that would mean that our 8m would go back here, and then would the m and the n have any common factor? No. So we could do that, but we can do better. We'd like to, if possible, have a common factor in the first half and a common factor in the second half. How can we do that? Let's put the 2n in the second spot. And then all the m's will drift back to the back. So let's rearrange this and write negative 3n squared plus 2n. Now those two have a common factor of n. And then we'll shift these to the back. Minus 8m and plus 12mn. Now there's a common factor of n here, and there's a common factor of m right there. Okay, now we're going to split it down the middle. Factor the left side. What can we get out of there? Just an n. We can factor out n, and we're left with negative 3n plus 2. And out of these two on the right, we can pull out a 4 and an m. Now, look what happens here. If we pull out a 4m, what are you left with here? You're left with negative 2, and you're left with here plus 3n, right? See, we got a minor problem, easy to fix, but note that these two don't quite match. We've got negative 3n plus 2, positive 3n minus 2. So how do you get those signs to line up the way you want them? Instead of pulling out 4m, you should pull out a negative 4m. That's going to change the sign on these, and then they'll match. So what we should do is we should factor out a negative 4m. You just got to watch that these parentheses value match up. Negative 4m, then this becomes a positive 2, and this becomes a negative 3n. Now, even though the terms are reversed, these two match. Negative 3n plus 2, negative 3n. So even though they're in a different order, they're the same thing. Okay, well, then we're done. We can factor those two out to the back, and we're left with n minus 4m times negative 3n plus 2. Wouldn't matter which order we put it in really, but we'll put the variable term first, negative 3n plus 2. No, before I underline it, is there any common factors in either of those? There's not. Drew? You could. Yep. There's a few different variations on this answer that would still all be true. This one definitely works. But there's a few different variations that would also work. You could have back here factored out a negative n. Then the signs here would be 3n minus 2. And then it would have worked to have just factored out the 4m here. So you might find, well, let's just look at a couple of variations on this that you could have had. If these signs were reversed, we could have had a negative 1 factored out, and then we'd have 4m minus n. Don't you agree that this is the equivalent of that? Okay, so watch out for that. The signs are different. Other than that, it's the same thing. Times negative 3n plus 2. Or we could have that negative sign back in over here, and that would be the same as 4m minus n times, negative sign could be in here, and it would be 3n minus 2. That would also be okay. So you're going to find that in your homework for today, that your answer might be very similar to the one in the back of the book, but the signs are different. Well, you may or may not be right. Go ahead and factor out a negative 1 and play with it and see if you can get it to match up. But they're all ultimately correct answers. Okay. Now let's just verify that this one is correct. Let's take this, let's go back to the original answer that we got here, and let's just verify that it does work out. Let's FOIL it out. Let's check it. So if we multiply this out, we're going to have negative 3n squared plus 2n plus 12mn minus 8m. Is that what we had? It is. Okay, so you can always know whether your factoring is correct because you can multiply it back out and you should get your original expression. Okay, so we can factor by grouping. All right, well, there's one other type of special case that we want to look at here. The sum and difference of cubes. Now, there's a way to remember. If you look at this, you might think yuck. Well, you should think yuck. Not might, ought to. But there's a way to remember those two factoring structures. Before we look at that way to remember them, let's just verify that they work. Okay, we won't do it with both of them, but let's pick one of them and verify that it works. Let's do the top one. We want to verify that a cubed plus b cubed is equal to a plus b times a squared minus ab plus b cubed. Well, how do you verify that that is the factorization? Multiply it out. Multiply it out, and we better be left with a cubed plus b cubed. So let's multiply these two out. Okay, if we multiply these out, I would say that this, you don't need to put this in your notes. It's just to verify that this works, okay? You should never take anything on faith. Maybe. Multiply that out. We get a cubed minus, let's see here, a squared b. Last term will give you plus ab cubed. That's not a cube. That's a, you all saw that like 2 minutes ago, didn't you? Nobody said anything. That should have been squared. You were going to wait for me to multiply that whole thing out, and then it wouldn't work. All right. It's squared. So now I'm glad I told you not to put it in your notes. So plus ab squared. That's right. Plus ba squared. Let's see here. Where can we put that? That's the same thing as this. Plus ba squared. minus ab squared plus b cubed. So we might multiply all that out and we're left with a cubed. Here, gone. Here, cancel, and so yeah, it works. That factorization works. You'd get almost the exact same result if we checked the other one, but we won't waste our time on that. They work very similarly. Now, how do you remember these factorizations? Well, there's not a lot of memorization, but this is one thing that you'll have to know. You won't come across factoring of cubes much, but I'll tell you you'll come across it once on the quiz when we get to this, so it'll pay to know them. But it's not that bad, actually. Just remember this pattern. Doesn't matter which one you're talking about. Remember that the pattern is the same. A cubed, b cubed, and it equals a and b, a squared, ab, b squared. It doesn't matter which one you've got. They both have that form. Now just remember the sign patterns. Which one do you want to do first, plus or minus? Good. Well, let's do plus first. If it's plus, the first sign is the same. If you're doing plus here, this one's plus. The second sign is opposite, and the third one is always positive. So if you want to know a cubed plus b cubed, we got plus, matches the original sign, opposite, and that one's always positive. If we want to do a cubed minus b cubed, we know it has to have this form, a and a b, a squared, ab, b squared. Well, if you want to figure out how to factor minus, this sign's going to be same, a minus. This sign's going to be opposite, so it's plus, and the last sign is always positive. And so the structure is almost exactly the same. Just remember the first sign matches what you're trying to factor, the second sign is opposite, and the third one is positive. So once we decide what's in the slot of A and the slot of B, then we can fill it into our structure and we'll have it factored. We'll do a couple of examples of that now. We'll start out with a small one and we'll progress from there. Okay, well, first of all, I'm just going to quiz you. Just try not to look at your notes. I guess it's not on the screen anymore. Just see if you can remember it, okay? What we want to factor here is this thing. We're trying to factor a cubed plus b cubed. We should verify, I kind of skipped this, but we should verify, are these both perfect cubes? Clearly the y cubed is. 27? Sure, it's 3 times 3 times 3 is 3 cubed. So now think about what is the factoring pattern for this? A cubed plus b cubed. How does that factor? The first set of parentheses has two terms. What are they? A and b. The second set has three terms. They are a squared, ab, and b squared. Okay, now the signs. Since we're trying to factor the sum of cubes, this sign is a positive. It matches. This sign is a negative, and the third one is positive. Okay, so once you know the factoring structure, you're good to go. Just like a difference of squares, you know is always a plus b, a minus b. Same principle, it's just a little bit uglier. Okay, well, in this case, we can rewrite this as 3 cubed plus y cubed. And so we can factor it according to, just fill in what we've got. What's the first binomial going to be? 3 plus y. 3 is playing the role of a, y is playing the role of b. 3 squared minus 3y plus y squared. Now that's factored, but you should simplify that just a pinch. The only thing really there that you can simplify is the 3 squared. So we would rewrite this as 3 plus y times 9 minus 3y plus y squared. That is factored. Now, this is a quick one to check. Let's make sure that we've got it factored right. Let's multiply this out. Your first term is 27 minus 9y plus 3y squared plus 9y minus 3y squared plus y cubed. So you end up with 27. Those are gone. Those are gone. Plus y cubed. Yep. It checks okay. We're good to go. Okay? All right. Look good? Let's do a couple more of those and we'll call it a day here. Let's factor this one. Actually, I'll give you a minute on this. Take a minute. I'll get it set up here and we'll work through it in a minute. But take just a couple of minutes and see if you can get this thing factored. Well, let's take a look. First of all, does everybody agree you've got a GCF of 2a there? Okay, pull that out. So you got 2a times 64a cubed minus b cubed. Now you kind of need to figure out what it is that you're cubing in each case. Clearly in this case we're subtracting off and we've got a b cubed in that spot. But what is it that's being cubed in this front slot? 4a, that's right. The cube root of 64 is 4. And the cube root of a cubed is a. And so 4a cubed, 4 times 4 times 4 is 64. A times a times a is a to the third. And so that's the way that this thing is really structured. Now that's playing our first term. This is playing our second term. And now we can factor it. Okay? All right. So let's do that. We've got 2a times. The 2a really doesn't play a role in how we're going to factor this difference of cubes. Now we're going to set up our general structure here. Okay, well, what are you going to have as the terms in your first binomial here after factors? 4a and b, and we want to match this sign, so it's 4a minus b. Okay? Now, what are you going to have here? 4a squared, or this first term squared, and so that'll be, I'm going to use another set of parentheses, 4a squared. What's the sign going to be? Plus, opposite of this one, so plus. Now what's your second term going to be? 4a times b. And your last sign is always plus, and it's going to be b squared. So now all we need to do is clean that up just a little bit. We have 2a times 4a minus b. 4a squared we would just write as 16a squared plus 4ab plus b squared, and that difference of cubes is factored. Okay? All right. Okay. First thing, GCF. What can you factor out of both? 3. And so we're left with 3 times 4x cubed minus 3y cubed. Good. Now what? What's that? That's it. You're done. It's the end of the line. To prove it, I'll put 2 lines underneath it. There, see? You're done. Why? They're not perfect cubes. It's tempting, but those are not perfect cubes. The variable parts are, but these coefficients prohibit them from being perfect cubes. We can't split this up into, we can't rewrite this, for example, we can't rewrite this as, like we did in the last one, we can't rewrite that as some package cubed minus some other thing cubed. The x would work, but there's nothing to put in here that would work. I mean, the cube root of 4, but that's not an integer, so you're done right there. Now, is that prime? Would we say that this thing was prime? No, you wouldn't say it's prime because you could factor it a little bit. But this factor right here is prime. This can't be broken down anymore. But to say that that's prime would be not true because we were able to factor it just a little bit. Okay. Watch for that greatest common factor. Pull it out in front. So we have 5 times p to the 6th minus q to the 6th. Okay, look good? Now, there's a couple different answers to the next question, but one that's the best. Are we done factoring? First of all, is that prime? Are we done? Is the p6 minus q to the 6th prime? It's not prime. That can be factored. What is it? How can you factor that p to the 6th minus q to the 6th? Close. Yeah, Drew's onto something here. You can factor out a p to the 3rd minus q to the 3rd. Is that a perfect square? It is. What do you square to get p to the 6th? In other words, what's the square root of p to the 6th? P to the 3rd. P to the 3rd times p to the 3rd is p to the 6th. Is that a perfect square? Yeah. Subtraction sign. What have you got here? Difference of squares, right? Square minus a square. That'll factor into 5 times difference of squares. Remember, any even exponent makes it a perfect square. So your first 2 terms have to be what? P to the 3rd and p to the 3rd. Now verify that. Well, we'll verify it in a minute. Your last 2 terms have to be q to the 3rd. Now you could quickly check it at this point. Foil this out. What's p to the 3rd times p to the 3rd? Remember, p to the 3rd times p to the 3rd, the reason that whole thing works is that that's p times p times p times p times p times p. So you end up with p to the 6th. That's the reason that the whole thing works. Why an even power up here makes it a perfect square. Okay, there, it's factored. Is that completely factored? No. That's beautiful. There's a sum of cubes right there. And over here, you got a difference of cubes. So, let's take care of this one first. P cubed plus q cubed. Q cubed. Okay, let's just take care of this first one. That's going to factor into what? What's your binomial here going to be? P plus q. The sign's going to match the positive. And then over here you're going to have your first term in your trinomial. P squared minus, yep, opposite sign, p squared minus pq plus q squared, yep. This is getting a little bit bunched up. I'm just going to rewrite it with a little bit more space here. 5. Okay, now we're not done. We still have to factor the p cubed minus q cubed. And so how's that going to factor? The first binomial here is going to be p minus cubed. This is the one we're working on now. P minus q times p squared plus pq plus q squared. Now, take a look at each one of those factors and make sure that none of those will factor. That won't factor, that won't factor, these won't factor. and neither will p minus q. You're done. Okay, that is completely factored. Okay. Questions about how we busted up that p to the 6 minus q to the 6 or factoring up the cubed? Okay, last one. I'm going to call it a day after this one. This one's a particular case. We have not dealt with any factoring where you've got a variable in the exponent yet. Let's just do one example where we have a variable up in the exponent. Okay, well, factor out your greatest common factor right off the top. Pull your 2 out of there and you get. Okay, now what are you suspicious of? The 6n. Yeah, it's starting to look an awful lot like what structure? Is that a perfect cube? Yep, it is. Is that a perfect cube? It's a good question. Is a to the 6n a perfect cube? Well, we can rewrite a to the 6n just a little bit. Okay, let's go over here for just a minute. This relies back on a few weeks ago when we did properties of exponents. You can rewrite that. A to the 6n is equal to a to the n to the 6th. Remember, if you have an exponent to an exponent, that's the same as just multiplying the two together. So a to the nth times 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 a to the nth, I think that's 6, gives you a to the 6n. Remember, the reason that's true, for example, is if you had x squared to the 3rd power, that's x squared times x squared times x squared, which is x to the 6th. That's the basic principle we're applying. So a to the 6n we can rewrite as a to the n to the 6th. So if we do that, if we rewrite that, this is the same as 2 times a to the n to the 6th power plus 64z to the 3rd. Now, is that a perfect cube? It is. What is that cubed? That's the same as 2 times. Let's rewrite these, breaking down our cubes. Now let's do the second one first. That's the easier one. What is it that is cubed to give you 64z cubed? 4z. Everybody agree with that? Just breaking this down so we can see our two parts a little bit easier. 4z cubed. What is it that you cube in order to get a to the n to the 6th? Nope, not an's. Well, you could say a to the n. You could say this. You could say a to the nth squared cubed. That's true. That gives you a to the 6n. You can multiply them all together. But that's the same as you can just multiply these two together, right? And say a to the 2n cubed. So we can really just say that that's, in other words, if we can break that up and break it into factors and put 1 on top, let's just leave the 2 there and put the 3 on top. Instead of pulling the whole 6 out, we can write that as a to the 2n cubed. That's a to the 6n because we could multiply those two together. Once we've got it written like that, we can factor away. So this is going to be equal to, running out of room here, let's go over here. That's equal to 2 times, okay. Well, what's your first binomial going to contain? A to the 2n plus 4z times, the trinomial out here is going to be a to the 2n squared, opposite sign, minus 4z a to the 2n plus 4z squared. And now we can just rewrite that and we're done. Let's stop there for a minute before we just square these two out. Everybody see the structure okay? That's our first thing cubed, that's our second thing cubed, and there they are. Good? Okay, well then we've got 2 a to the 2n plus 4z times, this becomes what? A to the 4n, good. Minus 4z a to the 2n. And the last one is plus 16z squared. And that one's done. That's factored. You're not going to come across that too often. But it's worth recognizing that that's how we can split up those exponents.